Welcome to section 17.4, and we're going to be talking about titrations of weak acids and weak bases. So let's go back to 17.3 for a second and remember what we were talking about before. We were taking something like KOH, strong base, plus HCl, strong acid, and we see this typical neutralization reaction where we get water and then the salt. In this case, K plus Cl minus. So in this case, these items over here do not affect the pH. So if you react a one-to-one amount of KOH and HCl, same molarity, same moles, or same amount of moles, they will produce a neutral solution. If you try to titrate them together with unequal amounts, let's say 2.0, say we're millimoles over here. Actually, let's just stick with moles for now. And react it with 1 mole of this. This will react, and you're left over with 1 mole of this and 0 of this. And the pH is determined by that excess OH minus. However, what if we are dealing with one of these being weak? So let's look at the case of, and this is going to be example 17.12 from section 17.4 in your online book. So in this example, we are going to react sodium hydroxide as our strong base, even put the state of matter in there, plus formic acid. That might look kind of weird, HCHO2. Formic acid, though, is this. It's the simplest carboxylic acid. Remember, we deal with acetic acid very often, which is just this CH3 group over here instead. This is formic acid, though, right here. So that's the structure we're considering. And we place this H on the left in our formula to show that is a acid. Let me get rid of all this stuff for a second. We don't really need to have this here. Want a little more room. There we go. So let's look at that equation over there. If these two react together, what are our products? Well, we're going to get water. We have these OHs and Hs reacting together. So what's our other product then? Well, it's going to be Na plus, and then the anion. In this case, the formate anion. So the Na plus will match up with the CHO2 minus species, and we'll get this sodium formate anion. So we're going to be neutralizing something with the acid or base here, but importantly, we need to remember if any of this is produced, we need to consider what that is. And remember, this is the conjugate base of a weak acid. This is a weak base, which could potentially affect the pH of our solution. Up here, though, KCl, Cl minus is the conjugate base of HCl. This is not a good base at all. It's not a weak base. So that doesn't affect our pH. However, this one does. So let's consider this problem, example 17.12, with that in mind. This problem starts with 40 milliliters of formic acid. And then we're going to be titrating it with a strong base. And the strong base is going to be sodium hydroxide. 0.5 molar. And this is also 0.5 molar, which is nice for stoichiometry here. And we're going to determine the pH. A. pH before adding NaOH. So like before, the pH of the solution will be determined by the molarity of the acid in solution. Remember, this is not a strong acid though. So how did we determine the pH of a weakly acidic solution? That's where we use our ice table. And remember that if this is what we have in solution to begin with, plus H2O, liquid, we have equilibrium here. We're going to produce a little bit of H3O plus, and then a little bit of our acetate ion. Aqueous. So initial, we've seen this many times before. Don't care about water. We have none of this and none of this. The change, X, because we have 1 molar in our coefficient here. So we're going to be adding an X over here and adding 1 mole over here. X and X. Importantly, though, we are missing one thing. We need the Ka of formic acid. So we're back to this situation. We need to solve for X. If we can solve for X, we can get the pH. X will equal our H3O plus concentration. So 1.8 times 10 to the negative 4 should be equivalent to X squared divided by 0.500. Remember, we're going to make the assumption that this X is so small that this basically equals that. And in the problem, the book actually says, assume that less than 5% of the acid ionizes in solution. So it's saying, go ahead and make that assumption. And that usually always works, but you always want to be careful. But we're going to assume this assumption works and proceed for there. Once we solve for X, we should get, well, we should do some math here, shouldn't we? But to save time, once you get X, X equals the H3O plus concentration. Take the negative log of X to get the pH. And our pH is 2.02. So first step in these titration problems is just to identify what you have to start with. Last time it was a strong acid. This time is a weak acid. So we were given the Ka, and using that, we can use our ice table technique. So we're starting at a pH of 2.02. I have some pre-made titration curves up here because I'm so prepared. And we've got milliliters of base added on the bottom. We're at 0 right here. And pH is just above 2. Now, you can imagine what will happen next. We are going to add a strong base to our solution. What's going to happen? Well, we'll be neutralizing some of the strong acid, and we're going to be producing some weak base over here as well. So let's analyze the next situation. And B in the book asks us to find pH at half. I think I spelled this wrong last time, but not today. There we go. Point. Remember what the equivalence point meant? That means we need to add exactly the amount of base to the acid to react it all fully. So a half equivalence point means we're going to add enough moles of NaOH to react with half of our initial acid. So how many moles of acid or millimoles of acid do we actually have? It says we started with 40 milliliters at 0.5 molar. So 40 milliliters times molarity equals 20 millimoles. Easy math. Don't even have to go to moles. So before reaction, we've got 20 millimoles. And it says at the half equivalence point. So we're going to add NaOH to this now. And we're going to add 10. 10 would be the amount that would react with half of our initial acid. Now remember, we have some products here that are important. We're going to get water. And we're going to get the sodium formate. Really, the CO2, actually, wait a second. Oh, that's good, CO2H. I'm missing an H, aren't I? CHO2 minus. Oh boy, getting crazy now. Still learning this software. Really cool software, but still learning. Okay, this is the important part. This CO2H minus anion. That's a weak base. So let's actually do our reaction now. This is our half equivalence point. We're adding 10 millimoles of NaOH. So a reaction is actually going to occur. So what happens? React in a 1-1 ratio. Who cares about water? The important after, this is what determines our pH. What is left over after this reaction? Well, we have 10 millimoles of this left over. All the sodium hydroxide is gone, and then we'll have 10 millimoles of this. Of basically CO2H minus. Sodium plus doesn't really do anything. It's just dissolved, remember, aqueous in solution. So how do we find the pH? We have to consider what we have left over. What's important, though, is to identify is that we have a buffer solution. So the NaOH is going to consume some of our weak acid, but we also produce some of this weak base, the conjugate base of formic acid. So remember, how do we find the pH of a buffer solution? All we have to remember is the Henderson-Hasselbalch equation. pH of a buffer solution equals the pKa of the acid plus the log of a ratio. What is that ratio? In class, we said the A is in the alphabet, it comes first. So we need our A minus BCs first up top and our HA. So let's see what we have. pH is going to be equivalent to, what's the pKa of formic acid? We have the Ka, it's up here. pKa equals the negative log of the Ka, which is that. And that is going to be 3.74. So let's come back down here. So I'm getting started small, and now I'm just kind of like zooming out and zooming out and zooming out. Kind of bizarre. I'm not quite used to this style of program yet, but it's kind of fun. So we've got the 3.74 plus the log of, what's my ratio of A minus to HA? Well, in this case, I could screw this up and put HA on top, but they both 10 millimoles. Remember, you don't have to have molarity in the Henderson-Hasselbalch equation because it's the same ratio. So we're just looking at the ratio. Remember, this is the special case, the half equivalence point, when I have equal amounts of conjugate acid and conjugate base. This is 1. The log of 1 goes to 0. So the pH should be simply 3.74. All this equals 0. So it's 3.74 plus 0. So that's what happens to the half equivalence point. So let's go back up to our tiny, oh boy, look at this, my tiny, tiny little graph way up here. That's okay. All scales, thankfully. So now we have added some amount of base. We don't have milliliters, but we know it's the half equivalence point. So this is now just about here. Half equivalence point. pH equals the pKa of formic acid. Now remember, if we'd added, I don't know, less base than that, we'd have a solution that's down here somewhere. So just below 3.74. So that's the first section of our titration curve for a weak acid reacting with a strong base. If we can continue to add more base, we get more of these dots. Let's say we have a couple more like that. I'm actually going to erase some of these. It just doesn't look great. Should simplify this a little bit more. Something like that. That'll be good for now. Okay, let's go back to the problem. So A again was pH before any NaOH was added. B is half equivalence point. And let me get back to the problem. Okay, C now asks us, what is the pH at the equivalence point in this case? Seven, right? No. 7 perhaps for strong acid, strong base. Don't think pH at every equivalence point is 7. pH for strong acid, strong base titations is 7. But for us, let's think about what this actually is asking us. If we have HCO2H plus NaOH before the reaction, B4, there we go, we had 20 millimoles. Now we're saying we're adding 20 millimoles. In this case, we always have to consider what we're producing and if those will have effect on the pH. H2O, no, but remember we've got all this weak base that we're producing. So there's our before. We're going to do a reaction. All of this reacts with all of this, and we're adding 20 millimoles over here. So after the reaction, unlike strong acid, strong base, where we would only have a neutral salt solution, we don't have any strong base or weak acid, but importantly, we have 20 millimoles of weak base. This determines the pH. So, got some more stuff to think about here. So what kind of problem is this now? This is a pH of a basic salt solution, analogous to the pH of a weak acid solution problem. So this is section 16.7. So it's kind of cool in this titration chapter, it's using stuff we've already used in the old units. So let's go ahead and do this problem. Where do we start? We have NaCO2H in solution plus H2O. A new equilibrium is formed where now H2O is going to donate an H to my base. Remember, sodium isn't really doing anything here. So I'm going to produce OH minus, and I'm going to produce the protonated form HCO2H. And yes, there's Na in here as well. But honestly, I just don't care about that. It's not doing anything. I'm just going to leave it out of the equation for now. So this is what's happening now. So I have a weak base equilibrium problem. We're going to produce a tiny bit of OH minus, but that's enough that's going to have a significant effect on my pH. So remember, this is just another ice table problem, initial change, etc. But it's going to look just like it did before. This time, though, it's the Kb because we have to think of this in terms of a base equation. So we need the equilibrium constant that refers to the base. Kb is equivalent to OH minus times HCO2H divided by our initial concentration, NaCO2H. So that's what we're thinking about again. So we need Kb. The top is again x squared. If we can get x, we can get the pH. Divided by, what was our initial concentration? That comes from the previous problem. So we need initial concentration of this stuff. So it's 20 millimoles that was produced. Divided by total volume. So what's our total volume of our solution? Let's think back to the problem. We had 40 milliliters of our HCHO2 I'm going to draw that zoomed in. And how much volume did we add over here? Well, the pH at the equivalence point means we added 20 milliliters of NaOH. So how much volume was that? Well, it has to match up with the volume of HCO2H because they're both at the same molarity. But we can also think of it like this. 20 millimoles times what was the molarity of our NaOH solution? It was 0.5. We go back up here, 0.5 molar. Our acid and base with the same molarity. If I divide by that molarity, this converts to milliliters. So yes, it's the same as the acid solution. So the molarity that I start with is 20 divided by 80 here. So that's the initial concentration that I need to do in this problem down here. Remember, there's usually an x here, but we're going to get rid of that and solve for x. And then we're going to actually solve for the molarity of our solution. What's the Kb? That's the last piece of the puzzle here. We were given Ka of formic acid. We can always get the Kb of the conjugate base by using the Kw expression. So Ka times Kb equals 1.00 times 10 to the negative 14th. So Ka was, let's zoom in here, 1.8 times 10 to the negative 4. All right, so if I divide both sides by 1.00 times 10 to the negative 4, Kb is going to be 5.6 times 10 to the negative 11. All right, that's an important number. That can now come down here. Now all we have to do is solve for x. And remember, POH equals the negative log of OH minus X is equal to OH minus in this equilibrium problem. So once I get the POH, which is going to be 5.43, the pH should be basic, so it's 14 minus that, 8.57. Whoops. So not very basic, but basic enough. It's a little bit basic because of this weak equilibrium problem. So the key to this, it says pH at equivalence point. That means I know I'm adding 20 millimoles of base to exactly react with the 20 millimoles of acid that I started with. Importantly, I produce 20 millimoles of weak base. So that turns this into a weak base equilibrium pH problem, where we start with this equation. You know what? I'm going to go ahead and erase this and just go ahead and write out the ice table here again. So we need an initial concentration of the sodium formate. That came from, again, the original problem. We produced 20 millimoles right here, and we had to remember that we added 40 milliliters of NaOH solution to reach the equivalence point. So our total solution volume was 80 milliliters, and this is the new molarity. This is our initial molarity of this right here. And we'll say we start with none of this, none of this. Minus x, plus x, plus x, 0.250 minus x at equilibrium. And then again, we simplified this by canceling that out. Substituted that into our equilibrium expression. Solve for KB rather. Solve for x. Take the negative log of x to get the POH. And then 14 minus the POH to get pH. A lot of little steps. We've done these problems before, though, in the last chapter, the last section. So if you don't remember how to do that, we're going to see it again in titrations. So you definitely need to be on top of this type of problem. Okay, we're getting there. Last piece of the puzzle. Step D. This says when the equivalence point has been reached and 2 milliliters of excess NaOH has been added to the solution. So pH 2.0 milliliters of excess OH minus is added. Well, at this point, pH is dominated by excess strong base. Past the equivalence point, there is a significant amount of weak base. We just saw that at the equivalence point there is. But because the pH is the OH minus is contributing so much to the pH, we simply just turn this into a strong base equilibrium or strong base pH calculation. So what do we need to know? Moles of OH minus. Let's delete that. Per total solution volume. First, we need the molarity of OH minus. So this says 2 milliliters of excess OH minus is added. And if we take that 2 milliliters, let's actually go ahead and convert that to liters. So 0.002 liters of NaOH is added. How many moles of OH minus was added? Well, we just multiply by its molarity. There's 0.5 moles per liter. So that's how many moles of OH minus is added. And we need to divide that by total solution volume. All we need to do there is remember that at the equivalence point, we had 80 milliliters of solution. That came from this fact up here. The equivalence point, we calculated the fact that we needed to add 40 milliliters of NaOH to 40 milliliters of our original solution. So now we're adding just a touch more volume to that. So total solution volume means 0.0020 liters NaOH plus 0.080 liters of solution. That came from that. So finally, OH minus molarity equals 1 molar, or 1 moles rather, divided by 0.082 liters of solution. And that gives us a molarity of 0.122 molar. So pH then, POH is negative log, remember this is of OH minus, equals 1.91 rather. pH is 14 minus that, 12.09. So now we just have excess sodium hydroxide completely dominating the pH. So if we go back up to our graph, which is, wow, look at this craziness. This is so cool. We'll zoom, zoom, zoom back in to all this mess. And we can take a look at this graph. Okay, what was the pH at the equivalence point? It was a little bit basic. It was like 8 point something. So the pH at the equivalence point, remember, does not equal 7. It's a little bit more than 7. It was, actually that's a little bit too high if you think about it. But we produced a solution of, let's go right about there. We produced a solution of a weak base at the equivalence point, and that's why it's not at 7. And after that, when we went past the equivalence point, we have excess sodium hydroxide. So the pH is just determined by the strong base. And that is going to be the typical pH curve for a weak acid being titrated with a strong base.